Okay. Good afternoon from snowy Montreal on this very chilly 22nd of April. Today, I have the honor of introducing Darcy Riley. Darcy received her bachelor's degree in mathematics and computer science from the University of Rochester. After graduating, she spent some time at Johns Hopkins University and at Google as a software engineer. She is now pursuing her PhD at l'Université de Notre-Dame-du-Lac, or as we call it in the United States, Notre Dame. Darcy's research studies the connections between formal language theory and probabilistic modeling. Out of the speakers we've had this semester, Darcy's research is probably the closest to our lab's area of research, and she's especially prepared this tutorial with our audience in mind. So I'm very eager for what should be a very vigorous and thought-provoking discussion today. Factor graphs unify many disparate topics in computer science, probability theory, and formal languages, and I could not be more excited to learn about some of those connections together with all of you here today. Will you please join me in giving a warm welcome to Darcy Riley?
Thank you so much, Brandon. Thank you for inviting me to speak here. I'm really excited to talk to you guys about my work. So this talk is going to be about factor graph grammars, which are a formalism that I've been developing with my advisor for probabilistic modeling. And so by probabilistic modeling, I mean two things. So it's a framework for probabilistic modeling, and by that I mean two things. It provides a language for expressing probability distributions, and it provides an automatic inference algorithm. So once you've specified your model, you can just automatically do inference. So that's what I'm going to tell you about in this talk. I'm going to tell you about those two things: the language for representing distributions and the automatic inference algorithm that we developed. So just as a really quick logistical note, because like the talk will build on earlier parts, like the formalisms in the later part of the talk will build on the formalisms in the earlier part, it's important that like everything's clear. So if anybody has questions, I invite you to interrupt me at any point in time. I'm going to pause for questions at the end of each section, but you don't have to wait until I pause. Feel free to just interrupt me whenever you have a question. Okay, so let me give you a quick overview of what I'm going to cover. So as you might guess from the name, factor graph grammars are an extension of factor graphs. So first I'm going to do a quick review of factor graphs and talk about some of their limitations. And so then factor graph grammars are made by combining factor graphs with another formalism called hyperedge replacement grammars. So I'm going to tell you about how those work. And once we've defined hyperedge replacement grammars, then I'll show you factor graph grammars. And then I'll show you one of the inference algorithms from our paper, which is an extension of variable elimination to factor graph grammars. And then I'll talk about a method that we've developed for querying a factor graph grammar. And finally, I'll briefly mention some related work and talk about some ongoing and future work that we're doing. So basically, all the content in this talk is based on a paper that my advisor and I published in NeurIPS last year. So if you're interested in any of the formal details, please check out this paper. Okay, so first, just a quick review of factor graphs. I think everyone here has probably seen factor graphs before. I know they came up in one of the previous talks in this series. But just as a reminder, a factor graph looks kind of like this, and it's made up of two things. It's made up of variables. These are the random variables in the model, and factors, which are a way of relating different variables in the model together. So each factor is associated with some function, and these factor functions will be multiplied together, and that's how you get the probability of an assignment under this model. So I'll come back to that in a minute, but first I want to make a quick terminological note about factor graphs, which is that I think a lot of people typically think of factor graphs as a bipartite graph. So it's got two kinds of nodes, variables and factors. We're going to think about factor graphs a little differently for the purpose of this talk. We're going to think of them as hypergraphs. So it's got one type of node, which are variables, and these nodes are connected to one another by hyperedges, which are an extension of the concept of an edge to more than two nodes, or even less than two nodes. You could have a hyperedge that connects to one node, a hyperedge that connects to 0 nodes. Those are my favorite, and I'll show you some later in this talk. So this hyperedge that we're currently pointing to, that's a 3 edge, and it connects to 3 nodes. And one further technical note, just like in a regular graph, a hypergraph can be directed or undirected. And so in a factor graph, all of the hyperedges are going to be directed hyperedges, because that's how you know in what order to apply the function to the arguments. And so, like, in principle, I should have written these numbers on all these edges to show you their ordering, but that clutters up the slide a lot, so I've left them out. But basically, every hyperedge that you will see in this talk is a directed hyperedge, and we just omit the numbering for not cluttering the slide. Okay, so let me give a quick review of how probabilities are computed in a factor graph. So if you want the probability of an assignment under this model, then you just multiply all the factors together. So if you just multiply them together, that gives you the weight. And if you want to convert that to a probability, then you have to multiply in some normalizing constant z. Because factor graphs are a globally normalized model similar to Markov random fields, unlike Bayes nets, which are a locally normalized model. So then how do you compute this normalizing constant z? Well, you just sum over all of the possible assignments to the graph, and then you just get your normalizing constant as usual. Okay, so before I move on to talking about some of the limitations, are there any questions yet about what we've covered so far?
I do have a question. So you mentioned that the factor graph is equivalent to a directed hypergraph. Is that what you meant?
Yeah.
So I don't see how this is, because usually in factor graphs you don't have any well, in standard factor graphs at least, you don't have a notion of direction, right? So that's where I'm a little bit confused that you are introducing direction in the hyperedges.
I see. Yeah, I see what you mean. You're thinking of Bayes nets, I think, where the direction on the edges sort of denotes a generative story, where first you generate some nodes, then you generate the others. So, okay, so yes, so that's directed in more of like a generative sense. In a factor graph, it's not, the directions on the edges don't give a generative story. It's just telling you, okay, like this is f of v4, v5, v6, not f of v5, v4, v6.
Oh, I see.
Yeah, it's just, if you're trying to read the factor functions off of the graph, you just need to know what order to apply them in, and that's all that's doing.
Okay, yeah, I got it. Thank you.
Okay, yeah, thank you for the question. Okay, so let me talk a little bit about the limitations of factor graphs. So first of all, factor graphs are pretty powerful. So related to what we were just talking about and how they connect to other probabilistic graphical models, factor graphs can represent any Bayes net, any Markov random field. So they're like fully general as far as probabilistic graphical models go. But there's still some things that they can't do. And in particular, they're limited by their fixed structure. And what I mean by this is that when you're defining a factor graph, you have to specify in advance exactly how many variables and factors it's going to need. Like that's just part of writing out the factor graph, is deciding those things. But sometimes you might want to model objects that have like a different number of nodes. So maybe sometimes it has one node, sometimes it has two nodes, and you don't want to decide that in advance. Sometimes you might even want to model structures which have an unbounded number of nodes, and factor graphs definitely can't do that. So the reason that we care about this is because factor graphs can't represent a lot of the models that we care most about in NLP. So in NLP, what we're typically doing is we want to build a probabilistic model over all possible sentences. And so this is like every single conceivable sentence in the English language, and we typically want to include one random variable for each word in the sentence, but these sentences have unbounded length. So you have no idea in advance how big of a factor graph you would need. And so you can't use factor graphs for that. So let me show you more concretely that factor graphs cannot represent HMMs. So I don't know whether people have covered HMMs before. So just very quickly, what an HMM is it's a model of a sentence where each word has a tag associated with it. And so there's like a chain of tags, and they're generated left to right. And then each tag generates a word. So it is typically drawn using a directed model, but since this talk is all about factor graphs, here is an HMM as a factor graph. And this factor graph here shows an HMM, it shows all sentences of length 1 that could be generated by an HMM. So in the middle, we have this variable T1 for a tag and a variable W2 for a word. And on the left and right sides, we have variables for the beginning of sentence and end of sentence token. Those aren't super important. What's important is that this factor graph here can only represent sentences of length 1. And if you want to represent sentences of length 2, then you have to add another word and tag. And if you want to represent sentences of length 3, you have to add yet another word and tag. So there is not one single factor graph that can represent every structure generated by the HMM. And I think this fact is a little bit underappreciated in NLP, because I have repeatedly heard people refer to HMMs as probabilistic graphical models. People say things like, oh, an HMM, that's just a Bayes net. Oh, the forward-backward algorithm for doing inference in an HMM, that's just variable elimination. And that's true for a fixed length of sentence. So if you know the sentence length, maybe you've already observed the sentence and you're just trying to figure out the tags, then you can use a traditional probabilistic graphical model. But if you want to represent the whole HMM, you need something else. And similarly, factor graph grammars can't represent PCFGs. But here, it's even worse, because in the HMM case, at least you only had one possible factor graph for every sentence length. In a probabilistic context-free grammar, if you want to represent like a sentence of length 3, for instance, on the slide, then there's 2 possible parse trees, and that corresponds to 2 different factor graph structures. So there's not even one single factor graph for a given sentence length. Are there any questions about this before I move on? Okay, cool.
Wait, just kind of a fuzzy question. So in some types of factor graphs, it seems like you're going to have just sort of the default assumption that each factor, each hyperedge here is going to be distinct. And in some of them, you're going to get sort of like a weight sharing sort of constraint. And is there any way that's being that will be represented in like the stuff that follows, like I don't know, different colors for different hyperedges or something like that?
Man, I probably should have drawn them as different colored hyperedges. That would be a good idea for a future talk. But yes, absolutely. There is going to be some weight sharing. So yeah, so we're going to generate factor graphs automatically, and we're going to generate them from sort of like a fixed grammar of little pieces of factor graphs. And so we'll only be able to include like a small finite number of possible factor functions that will appear multiple points in time. So yeah, on this slide, I should have written this in somewhere, but like these, can you guys see my mouse?
Mm-hmm.
Okay, cool. Yeah, so like all of these three edges, these are all representing the same factor function.
Okay.
So yes,
Cool,
that's
thanks.
a very good question. Thank you. Okay, so so the solution that we came up with for extending factor graphs that they can handle these cases we just talked about, HMMs and PCFGs, the solution is to use hyperedge replacement grammars. So one insight that we sort of had while thinking about the HMM example and the PCFG example is like, okay, well, you can't represent an HMM as a single factor graph, but it looks like you can sort of represent it as a set of factor graphs. And same with PCFGs. It looks like you can sort of represent it as a set of factor graphs. So that's what a hyperedge replacement grammar does. It's a method for describing a set of factor graphs. And I'm going to show you what those look like right now. So, so just as a super quick review, remember how context-free string grammars work. You have these rules. They all have a left-hand side and a right-hand side, and that tells you how to replace non-terminals with little fragments of strings. So you start with the S symbol, and you just keep replacing non-terminals with fragments of strings until you've run out of non-terminals. And so we are going to do the exact same thing, but with graphs. So this is what a hyperedge replacement grammar looks like. It's just like in a context-free grammar, it has rules, and each rule has a left-hand side and a right-hand side. And now it's just that the left-hand side is a non-terminal hyperedge, and the right-hand side is a fragment of graph that we're going to replace the hyperedge with. So let me walk you through an example. So we start out at the beginning with just a single non-terminal hyperedge labeled S. And this may not look like a hyperedge to you because it is not connected to any nodes, but what this is a zero-array hyperedge, a hyperedge that connects to 0 nodes. And so now we're just going to replace it using one of the rules from our grammar. And there's only one S rule, so it's really easy to pick that one. And so let's just replace our S hyperedge with this graph fragment. Cool. So now we have a graph fragment that has one non-terminal hyperedge in it. And so we're going to replace that. And we have 2 A rules that we can choose from in our grammar. So let's go with the first one. And something really interesting is going to happen when we replace this hyperedge. So as you'll notice, like in the graph, A is connected up to this node by 2 tentacles. Sorry, these are not called edges because A itself is the edge, so the little things that attach to the nodes are called tentacles, and I did not make up this terminology. This is standard terminology for hyperedge replacement grammars. So okay, so when we replace A, what happens to this node that A is connected up to? Well, it turns out that the rules tell you exactly how to handle this. So the left-hand side shows that it's connected to 2 nodes. This just tells you how many tentacles A has. And then on the right-hand side, we see 2 nodes in a darker color. These are called external nodes, and they show you basically, they say like when you replace A, take the 2 nodes that A is already connected to and match them up with these 2 nodes in the right-hand side. And since A is only connected to 1 node, they'll both get matched up to, sorry, both of these rules in the right-hand side will get matched up to that one. So it's easiest if I just show you how it works. So there, we've replaced it in, and you see that the new A is now connected by both of its tentacles to that same original node. So, okay, now we're going to replace A again. And again, we can choose from two different rules. I'm going to pick the first one again. And this time, since our current A non-terminal is connected to two different edges, sorry, connected to two different nodes, when we add in the new graph fragment, it'll be connected to those two different nodes. Okay, so we continue with this process, continuing to select which rule to replace A with and replacing it. And when we get to this point, I'm finally going to choose that second rule, and I'm just going to replace A with that. And now we have a graph that has no non-terminal hyperedges left in it. So we're done generating, and this is our terminal graph. And so in general, this particular hyperedge replacement grammar generates the language of all ring graphs with one or more nodes. So are there any questions about how that works?
It looks like the nodes are not labeled here. Do you have a version where they are, or is if you'd like to have a rule that specifies the node is two different nodes, is that possible to express? Or unique? So for, say, the second one, if you wanted those to be unique nodes that are connected to the tentacles.
Yeah.
Is that possible?
Yeah, so that is a really, really good question. And is another one of these things that I left off the slides just to keep the drawings tidy. But yeah, so I've labeled the non-terminal hyperedges. I have not labeled the terminal hyperedges, but in theory, all of them do have some label. I'm just sort of assuming in this example that they all have the same terminal label. We could call it A, and since it's all the same, I didn't bother to write it. But yeah, so each one of these squares should maybe have a little lowercase a in it. As for node labels, the original hyperedge replacement grammar formalism did not include node labels. All nodes were of the same type. But when we extend it to factor graph grammars, node labels are going to be one of the things that we add to the formalism. And it's pretty straightforward to add. It doesn't require any modification to the formalism. All you do is when you're writing out the right-hand sides, then you put the node labels in. It really does not complicate the formalism or require any changes to the method for generating graphs using the grammar.
Okay, thank you.
Yeah, thank you for the question.
So I had a quick question, a quick comment. So the question is it legal to have rewriting rules where you delete a hyperedge? Like if, for example, if we wanted to get like the collection of line graphs, then it would be like legal to have the second rule just take A and just get rid of it and leave two nodes there?
Yes, absolutely.
Okay. And then the comment is that actually there's a sort of graphical formalism called Tensor Networks, which is kind of dual to all of this stuff. And people have studied hyperedges in that context. It's a little bit different because the hyperedges there would correspond to the variables here. But in that context, people call them spiders. So just letting you know, it's other creepy, crawly, multi-tentacled creatures. I don't know.
Thank you. I appreciate that. I did not know about spiders, and as a mild arachnophobe, I think I have to say that I prefer tentacles. What I really don't want to encounter is a spider with tentacles.
Yes, yeah. Pick one or the other, I guess.
But yes, thank you for the question. And yes, absolutely, you can delete a hyperedge in the right-hand side of a rule. You can also have a rule that has multiple non-terminal hyperedges on the right-hand side. We'll see that in one of the factor graph grammars, but I just kept this example like super ultra simple. But yeah, you can do much more than this example does.
Okay, thanks.
So One final quick note on hyperedge replacement grammars before I show you factor graph grammars themselves is that I wanted to answer a question that I remember Brandon had when we talked earlier. Brandon, I think you asked, like, how did we come up with the idea of using hyperedge replacement grammars with factor graphs? Like, where did that come from? And the answer is that hyperedge replacement grammars have actually been used in several places in NLP. So I just wanted to mention that quickly. I think they sort of got introduced into the field of NLP maybe around 2011 or 2012 when people started using them for machine translation. So one of the things in NLP is that we often represent semantics using graphs. So like the sentence will just be a string, or its syntax will be a tree, but maybe the semantic structure is more of a graph or a DAG. I'm not going to show you any of these semantic graphs in this talk, but people use them. And so people started thinking like, well, how do you simultaneously like parse the sentence and convert it to a graph? And so people were using synchronous hyperedge replacement grammars to do this. And they were using that graph notation as an intermediate for machine translation. They were using it just for pure parsing into a semantic representation. And so there had been some pre-existing work in NLP on hyperedge replacement grammars. And actually, my advisor had published a paper in 2013 on how to parse them more efficiently. So we are not the first people to use these in NLP. So we're building on that previous work.
Yeah, that's great. I think that makes a lot of sense to have syntax and semantics kind of using the same structures, and it's great to have that historical perspective. Thanks.
Yeah, if you're interested, I can send you the paper later. It's cool. So yeah, okay. Now that we have seen both hyperedge replacement grammars and factor graphs, it is pretty much trivial to define factor graph grammars. They are just a hyperedge replacement grammar that generates factor graphs. And we really don't have to add like any extra machinery to get this to work. The only extra machinery that we add is, as mentioned earlier, now nodes have labels. So this is a hyperedge replacement grammar. Sorry, this is a factor graph grammar that's equivalent to an HMM. So just like in our HRG, it has left-hand sides and right-hand sides, but now these are all fragments of factor graphs rather than just fragments of ordinary graphs. So the nodes have labels, and each node label corresponds to a particular domain that a variable can range over. So like T, like all the nodes labeled with T range over some domain of tags, which could include noun, verb, determiner, etc. All of the nodes labeled W range over words in the language. So when you have a factor graph grammar, you have this like fixed library of node types that you can include. And so every variable in the generated factor graph will have one of these types. And then relating to one of the questions from earlier, all of the terminal edge labels will now be associated with particular factor functions. So the rule says how each terminal edge label is related to a factor function. So really there should be like a little function drawn on top of this relating T1 and T2. But again, I left it out to keep the slides less cluttered. But if you want to see it, you can look in the paper. We do draw it in the paper. So let me generate something for you with this grammar. So yet again, we start with our start non-terminal S, and we replace it using one of the rules. And yet again, there's only one S rule. So we go ahead and replace it with that. And now we have one non-terminal hyperedge. We're going to choose the first rule. And so now we replace it, gluing the external node in the darker yellow to the green node that X is currently attached to. And now, yet again, we have one non-terminal labeled edge. So again, we replace it, and let's use the second rule this time. So now we plug it in, and now we have our finished graph, which has no non-terminal hyperedges. And this, as you can see, is the factor graph for sentences of length 1 that we saw earlier. So in general, this grammar can generate the factor graph for any length of sentence, and therefore it describes, since it describes all possible lengths of sentences, it corresponds to the entire HMM. Do you guys have any questions on that?
So I do have a question, but I think it's more related to hyperedge replacement grammar in general, and I forgot to ask it earlier. Sorry. So is there any limitation to using an hyperedge replacement grammar? Like this is, as far as I understand, this is the counterpart to CFGs. Is there like any language of graphs that we can't express with some kind of hyperedge replacement grammar?
Yes. So I don't know as much about this as I'd like to. There's a whole literature out there, I think probably about formal languages over graphs, and hyperedge replacement grammars are the only ones I know so far. But I can tell you one very specific class of graphs that they can't generate, which is graphs with unbounded tree width. Are you familiar with tree width?
Yeah.
Yeah, okay. So you see that like each of the rules, like all of the factors have a fixed number of nodes that they attach to, and just based on that and the way the generative process works, you're never going to get an unbounded tree width. The tree width is very strongly constrained by the structure of the rules. So you cannot generate the language of all complete graphs with any number of nodes.
But this is good in the context of factor graphs, right? Because you don't want to have an unbounded tree width.
Yes, precisely.
Okay, that's cool. Thank you.
Thank you so much for the question. I really appreciate everybody asking questions. Okay, so now I'm going to show you another one. This one's for PCFGs, and this one's exciting because we're going to have our first rules that have two non-terminals in the right-hand side. So just super quick notational note, this vertical bar here just means or. I didn't have room to stack all three of the rules in a vertical column, so I just put this or between them, similarly to how CFGs are frequently written. So as usual, we start with our start symbol, and we replace it. Here's our rule with two non-terminal hyperedges. So now we have to pick which one of these non-terminal hyperedges we're going to replace. And I'm just happening to pick the left one. The order doesn't matter because it's context-free. You can replace them in any order and you'll get the same graph. And any order that you replace it in, that's all considered just the same derivation. It doesn't matter what order you go in. So I'm going to replace that one with this rule. And now I'm just going to go left to right, and I'm going to replace all of these remaining X rules using the second X rule. And then we're done. And here is one of the parse trees for sentences of length 3 that we saw earlier. So lest you hear this talk and think that FGGs are only good for representing these sort of formal languages theory things that we like in NLP, I wanted to tell you some of the other things that you can use them for. So you can use them for like simple little graph structures like linear chains of nodes or the ring graphs that we saw before. You can use it for anything tree-shaped, as long as each node in the tree can have like a bounded number of children. And actually, I'm not even sure if that's a constraint. So, but like any tree thing from like any field, phylogeny trees, abstract syntax trees, etc. You can do more grammatical formalisms. So I'm not quite sure yet about like exactly how powerful FGGs are in terms of the Chomsky hierarchy. I know that hyperedge replacement grammars are able to represent LCFRS, which is like the most general, mildly context-sensitive formalism. But that's like if you're generating a graph that ends up as like just a big chain and then you read the string off the chain. So I'm not totally sure what the formal power of HRGs is, and that's something to explore more in the future. But you can represent various types of DAGs. AMRs are the semantic formalism from NLP that I mentioned earlier. You could also do control flow graphs, maybe get commit histories. I don't know. I was just coming up with some ideas for things people could use these for. And I'm not super familiar with RNA secondary structures, but I know that they're something from computational biology, which could also be represented using a factor graph grammar. Okay, any questions before we talk about how to compute probabilities in factor graph grammars?
I was wondering if you know whether it can represent this CCGs or combinatory categorical grammars. I guess you can kind of count repeated things, or is I guess that might be a little bit more than context LCFRS. I'm not sure, but it seems like. Yeah, if it can just represent these up to cycles and DAGs, then that's pretty expressive for a lot of applications, and it's reasonably tractable.
You said combinatory categorical grammars?
Yes.
Yeah, so I think you can represent them. So tag, which is one of the things you can represent, is weakly equivalent to CCG, in that they can generate the same sets of strings. However, they're not strongly equivalent. I know that tag and CCG generate different tree languages, and so I'm not sure. So I know that factor graph grammars can generate the tree language generated by tags. I'm not sure about the tree language generated by CCGs, and that's a really interesting question.
Thanks.
Okay, so let's talk about how to compute probabilities using a factor graph grammar. So remember this slide that we saw earlier of computing probabilities in just a regular old factor graph. If you want to compute the weight of an assignment to nodes, you just multiply the factor functions together. If you want to turn it into a probability, you normalize by the normalizing constant z. And if you want to compute z, you just sum over all the variable assignments. And this normalizing constant z is also known as the sum product. So I'm just going to refer to it as the sum product for the rest of this talk. So, so now suppose that you want to do the same thing for a factor graph grammar. Suppose that you have some graph generated by your grammar, and you want to know the weight of some particular assignment to this graph. Well, you just multiply the factors together once again, and that gives you the weight. And if you want to turn it into a probability, then yet again, you just multiply in the normalizing constant 1 over z. So then the real question is, how do you compute z, the normalizing constant or sum product for the whole factor graph grammar? And the answer is that first, we're gonna think about all of the graphs that could be generated by this grammar. And we're gonna take the sum product of each one using the formula from factor graphs from a couple slides ago. So we're gonna, for each one of these graphs, we're gonna sum over all possible assignments and get its sum product. And then we're gonna add all of these sum products together, and that's gonna give us the sum product of the whole factor graph grammar. Does that make sense? I'll take that as a yes. Yeah, so a few things to note here. This is a sum over derivations, not a sum over graphs. So if your factor graph grammar is ambiguous and it can derive a particular graph in multiple different ways, then that graph will appear multiple different times in the sum. The second note is that all of these graphs that we generated have equal weight in the sum. We don't have any weights on the factor graph grammar rules. They just generate graphs and then you sum over the sum products of the graphs. If you want to add weights to the FGG rules, it's really easy. You just add another like standalone zero-ary factor in the right-hand side, and you can have that just multiply in the weight for that rule if you want to do that. Which is why we left it out.
Yeah, for this sum, if this converges to like a cycle like you saw earlier, then maybe you could do the normalizing constant over that, because or if it's unbounded, if it just kind of keeps growing and growing, does this become a problem?
So that's a good question. I think if I'm understanding correctly, I think what you're getting at is like, could this be an infinite sum here? So the sum product for any individual factor graph is going to be finite. If it's just a normal factor graph, you just take the sum product and it will be finite. But your grammar might generate an infinite number of factor graphs, and so this sum here will be an infinite sum. And that's definitely the case for HMMs, because HMMs can generate one factor graph for each sentence length, and sentence length is unbounded. So yes, you cannot compute this directly. This is more just for the purpose of like defining Z. How we actually compute it is going to be using an inference algorithm that I'm going to show you in a moment. But yeah, even when you can compute this sum directly, even when there are a finite number of factor graphs, it's it's going to be really computationally expensive to do that sort of brute force computation, and so you definitely want to use a more efficient algorithm.
I see. Thanks.
Let me just check how we're doing on time. Okay. Looks like we're running out of time, so I'll try to go through inference quickly. So in our paper, we talk about 3 cases for inference. We talk about the case where it's an infinite graph language. So the grammar might generate an infinite number of graphs, and therefore that Z sum is going to be infinite. But if all the variable domains are finite, so if like it's a variable that ranges over like a fixed set of tags rather than over the entire set of natural numbers or something, then we can use an algorithm which we've developed, which is an extension of variable elimination. If we have a finite graph language, but the variables have infinite domains, so they range over natural numbers or continuous numbers, or real numbers, then what you can do is convert your factor graph grammar to one gigantic factor graph and do inference over that. And then in the third case, if you have both an infinite graph language and infinite variable domains, it turns out that inference is undecidable, which we prove in our paper. But in this talk, I'm just going to show you the first case where we do an extension of variable elimination. So the way we're going to do this, so we need to compute Z, and in order to compute Z, we're going to write down a system of equations that lets us solve for it. And so, as you might expect, this system of equations is based on the grammar rules. And we're going to have one equation for each left-hand side plus assignment to external nodes, plus one equation for each right-hand side plus assignment to external nodes. So I'm going to show you what that looks like. So these are the equations for the left-hand sides. And what this is saying is, like this Z of S here, this is representing the total weight of all graphs that can be generated starting from the S hyperedge. And as it happens, that's all possible graphs in this grammar. So this Z of S will be the total sum product that we're looking for. And so how do you compute it? How do you compute the total weight of all graphs generated from S? Well, it's simply the total weight of all the graphs generated from the right-hand side of the S rule. And it's very similar for this X rule. Suppose you want to know all of you want to know the total weight of all of the graphs that can be generated starting with the X non-terminal. Well, it's the total weight of all the graphs that can be generated starting from the first right-hand side plus the total weight of all the graphs that can be generated from the second right-hand side. So the only thing to note here that makes this a little bit odd is that we're going to have a different copy of this X equation for every assignment to this external node T1. So that's why I've written it in a lowercase letter to indicate that it's a specific instantiation of T1 and not the random variable in general. So that's why it has to be finite variable domains, because we're going to make a copy of this equation for each thing in the variable domain. Does that make sense? I realize that this might be the sort of thing that people have to stare at for a little while before it makes sense. Okay, so now I'm going to show you the equations for the right-hand side. So this is what we just saw before. This is the total weight of all graphs that can be generated starting with this right-hand side. And what is that total weight? Well, it's a sum over all, so like it would be a sum over the weights of all these graphs. And we can sort of factor this out like we do in variable elimination. So we sum over all assignments to T1, and then we multiply in the product, we multiply in the total weight of all the graphs that can be derived if we assume that that the assignment here is T1. And that's basically the same principle throughout. Here, when we get to a terminal right-hand side with no non-terminal symbols in it, then you can see there's no z of anything in this equation. And then our last equation, just for the sake of completeness, looks like this. And so the unknowns in our equations, oh, sorry, this is also supposed to have another term for x in it, and I completely left that out of this picture, and I apologize. So I'll go back for a second. So these z's and this here, these are the unknowns in our system of equations, and we have to solve for them. What is the complexity of inference, you might wonder? Well, it's going to depend on how many equations we have in our system of equations. So we're going to have one equation for each left-hand side and one equation for each right-hand side. So that's captured by this size of G, which is the size of the grammar, which is the number of rules. And then for each rule, for each rule, then we make a bunch of copies of it depending on how many assignments there are to the external nodes. So suppose our external node is some variable t that has maybe like 5 possible values. Well, if we have one external node t, then we'll have to make 5 copies of the equation. If we have 2 external nodes, then we'll have to make 5 times 5 copies of the equation. And so that's where we get this m to the k. So we have size of G times m to the k equations in our system. And when we're solving this, there's a few cases. If our grammar is non-recursive, so there's no loops, like if you have non-terminal x, you can never generate a graph that contains an x anywhere in it, then you don't have to use any fancy equation solving mechanisms. You just plug it in, like solve each equation individually, plug them into the earlier ones, etc. If it's a system of linear equations, you can solve it, and that'll just be the number of rules cubed. And otherwise, you have to solve it iteratively. So I realized this went very quickly, and this is probably the sort of thing that you got to stare at for a little while. But does anyone have questions about inference?
Can you give an example where it cannot be linear?
Yeah. So So let me go back to, actually, I'm not going to go all the way back in the slides to the probabilistic context-free grammar example, but that's one of them. You have like, actually, maybe I should go all the way back. So here you see you've got x and it generates like 2 x's. So then when you write out the equation for that, it's going to have this term z of this rule multiplied in twice. And so that's a quadratic equation.
Okay. Thank you.
Okay, so I know we are running out of time, so I'm going to go through this quickly because I want to finish by 2:30. But let me show you very quickly how we might query a factor graph grammar. So in an ordinary factor graph, we often want to do queries. That is, we want to like maybe observe the values for a couple of nodes. So I've added a couple of factors on the bottom there. And those factors can be used to constrain the value of those nodes to some particular observation. And then maybe we want to query these nodes and get their marginal distributions. And in order to do that, then we sum out the remaining variables in the graph. So how do we query a factor graph grammar? Because right now I've showed you a method of computing the sum product, and so you can use that to compute the probability of an individual assignment to an individual graph. But if you want to query something, what do you do if, say, you want to like observe a value for the second to last tag? Like maybe you want to say like the second to last tag was a verb. How do you express that? Well, this is kind of tricky because the second to last tag is going to appear in a different place in each one of these graphs. And so it's really hard to like definitively like point at the graph and like specify which one the second to last node is, like in an abstract way. So the trick we came up with was that instead of trying to identify nodes in the graph, we're going to identify nodes in the grammar. So here's our grammar again. And we're going to take the second rule and we're going to split it in half. And we're going to make a copy of it. And then we can write out this new grammar that is constraining the second to last node to be a particular value. So I put this extra factor on here, which constrains the second to last node to be a particular value. And this is the second to last because like you'll be generating starting with X and you'll go through and you generate this a bunch of times. And then finally, when you use this rule, you only have one choice left, and that's to use the Y rule, which ends the generation. So this is guaranteed to be the second to last tag. So now suppose you want to compute the probability that the second to last tag is a verb. Well, then you compute the sum product for this grammar on the right-hand side, and then you divide it by the sum product of this grammar on the left-hand side. And that's how you do that computation. So it is kind of a pain to rewrite your grammar every single time you want to do a query. And so we developed something called conjunction, which you can read more about in the paper, that lets you modularize your grammar into 2 halves, an original grammar and a query grammar. So this is what this might look like. And then you conjoin them using conjunction, and it automatically combines them into a single graph. So you can read the details about this in the paper, but the important thing is that in order to query it, you specify a new grammar that constrains the things you want to constrain. So before we wrap up, I want to tell you a little bit about related work in this domain of extensions to probabilistic graphical models. So there's been lots of previous work in this area. There's been a bunch of tractable formalisms developed, such as plated factor graphs, case factor diagrams, dynamic graphical models, sum product networks. And these are all, these are all less powerful than factor graph grammars. None of them can generate both an HMM and a PCFG. And then you have really expressive formalisms like probabilistic relational models or probabilistic programming languages. And I know a lot of people here are interested in probabilistic programming languages. So these formalisms are very, very expressive, more expressive than factor graph grammars, but inference is often intractable. There's not necessarily algorithms for exact inference. And so we feel that factor graphs sit at sort of a sweet spot between these. As I said, they're more powerful than the 4 tractable formalisms that I mentioned earlier, but they also still have tractable exact inference in a lot of cases. And so obviously factor graph grammars are not going to be like the thing you want to use for everything. If you can solve your problem just using a regular old factor graph, like by all means, go ahead and do that. But we feel that factor graph grammars fill a really important gap along the trade-off from tractability to expressivity. And so now I'm just going to tell you a tiny bit about ongoing and future work. So this is ongoing work that I'm not directly involved in, but because I think you guys will find it particularly interesting, I wanted to make sure to mention it. This is a project that my advisor, David Chang, has been doing with his collaborator, Chengqie Shan, and they are building a miniature probabilistic programming language that compiles down to a factor graph grammar. So if you looked at factor graph grammars and you thought, like, that's cool, but I'm not accustomed to writing graph grammar rules, so it might take me like a while to write one of these things. Well, this is what you might be interested in, because now you can specify factor graph grammars in a much more natural programming language like syntax. So I can't present this work in any detail, so you can check out their archive paper on this. They presented it at Prague 2020, and just as a sneak peek, here is a picture that I copied out of David's Prague talk, where he defined a program for sampling from a PCFG and then automatically converted it to a factor graph grammar that looks a lot like the PCFG grammar that we saw earlier in this talk, except now it's sideways and it's got a little bit of extra stuff in it. So that is ongoing work. David and Chengqie are working on this. And then some future work that I'm particularly interested in doing is, okay, so one question that I get every time I tell people about factor grammars is, cool, so are they implemented? And the answer is not quite yet. We are working on this. I am in the process of implementing them. And I hope to at some point soon have a Python library to release for factor graph grammars. And ideally, this Python library will be compatible with PyTorch, but this is a work in progress, so stay tuned. I am hoping the implementation will be out soon. A second really important piece of future work is approximate inference. So I showed you an exact inference algorithm, and it is tractable in lots of cases, but maybe your grammar has high tree width or very big rules, and you don't want to do the whole exact inference algorithm. Well, then it would be really great if we had some approximate inference algorithms you could use. So that's a big open question. Another question is, are there better ways to query factor graph grammars than building a new grammar and doing conjunction? Because conjunction it can't necessarily specify all queries, I don't think. I think there's some that would be hard to express using conjunction. And so we're interested in more general querying mechanisms. And then one thing that's really like a long-term kind of thing, very speculative, is automatic structure learning for factor graph grammar rules. So normally, like when I present factor graph grammars, I'm usually presenting it as like a language for you to write in. Like you have some distribution, you know what it is already, you write it as a factor graph grammar, and then you learn the weights. But it would be really cool if you could automatically learn the factor graph grammar structure. And this would be similar to like automatically learning program structure. So really hard, but it would be super cool. So that's it. That's a bunch of the future work that we're hoping to do. This is fairly new work. As I said, we just published this in NeurIPS 2020. So this is like a brand new formalism. And so there's lots of really exciting stuff left to be done on it. So stay tuned for this future work. And thank you so much, everybody, for coming to this talk. Thank you, Brandon, for having me. And thank you, everybody, for asking questions. I really appreciate it. And so that's the entire talk, but I can stick around and answer questions as long as anyone would like.
Okay, great, really great. This is so thanks for this very lucid presentation, and it might take a few rewatchings to get all the details, but I know we put a lot of effort into putting together these figures, and that's very appreciated. I'll ask everybody to unmute and please give a round more applause to Darcy.
Thank you, guys.
Okay, if there are any questions now, audience, take it away.
So I'm curious to hear how far you are in this approximate inference on factor graph grammars, because it seems like the standard extension of variable elimination to factor graph grammar, it might be scalable, but up to a certain point and for certain rules. So if you have this seems like a really, it would be a great tool to really enable factor graph grammar for everyone. So do you have any anything that you like, any ideas of directions that might be worth looking at for this?
So yeah, I fully agree about the importance of approximate inference. It's absolutely something that we need to do. I don't know yet. I have actually been, ever since we published the paper, I've been taking a short break from factor graph grammars to work on a different project. And so I have not been working on approximate inference, even though it's my next priority for the factor graph grammar project. So the short answer is no, I don't yet know how to do approximate inference. It's pretty straightforward to sample both factor graphs and specific assignments to factor graphs from a factor graph grammar, but that doesn't really get you that far. So, so yeah, this is a really important open question. I think like we should be able to develop like MCMC sort of sampling algorithms for it. I haven't yet, but I have the sense that it should be pretty doable. I'm less sure about how to extend something like loopy belief propagation to factor graph grammars, because you'd sort of have to do it within the system of equations, and I don't yet know how to do that.
Yeah, maybe in the case where you have only like a finite, you can generate a finite amount of graphs, and then you can write everything as a like big graph like you did before, and then you apply loopy BP on top of it, and that's probably gonna work fine. But yeah, the problem is like in any other cases, and I assume that you don't want to build this like very big, very large factor graph in the first place. So that's really interesting.
Yeah, so we actually talk about that a little bit in the paper. So the second inference algorithm from the paper, which I didn't show, it is converting an FGG to one gigantic factor graph. And yes, you can do loopy belief propagation on that, but that factor graph is really big and unwieldy.
You don't want to.
Yeah, no, you really don't want to. So yeah, so definitely lots of work to be done on how to make that better. Any other questions?
Yeah, so I didn't have a specific question. I actually had a bunch of different questions, and I just want to say, at some point, like it would be awesome to talk more about this, because a lot of this overlaps with the work that I'm doing here in the group of Guillaume Rabousseau. And so it'd be good just to, I mean, it's very different, like terminologies, different communities, but I think a lot of the techniques that have been developed in my field could be helpful for like some of the approximate inference stuff. And vice versa, there's a lot of things that I'd like to learn more about with this. So I don't know if it's all right with you, I can send you an email at some point and I don't know, set up a time to talk or something.
Absolutely. I'm generally around and I would absolutely love to talk more. Yeah, if you could even send me links to some of the papers from your area, I'd love to see them. But yeah, I would be happy to set up a meeting at some point in the future.
Perfect. Looking forward to it.
Okay, well, maybe if we end the recording now, and then maybe there'll be other questions if you'd like, or I think let's end on a strong point. Thanks again, Darcy, for this really great talk. It's generated a lot of interest, and I'm happy that had the chance to hear about it today. This is fantastic. Thanks.
Thank you guys so much. You are like the best audience that I could have asked for.